Suppose the charges of two conducting plates of the charged capacitor are plus Q and minus Q at any moment. The potential difference between the two plates is V. If we want to take a very small charge dq from the negative plate to the positive plate of the capacitor, then the work required in doing so is dW is equal to V dq. That is equal to Q upon C into dq. Hence, the work done to deposit the charge of value from Q is equal to 0 to Q is equal to Q on the capacitor, W is equal to integral 0 to Q, Q upon C dq. Is equal to Q square upon 2C. The energy of the amount Q square upon 2C is stored in the capacitor having charge Q. Now Q is equal to CV. Therefore, W is equal to Q square upon 2C is equal to C square into V square upon 2C. That is equal to half CV square. For series combination, W is equal to Q square upon 2C, that is equal to Q square upon 2 into 1 upon C1 plus 1 upon C2 plus and so on, is equal to Q square upon 2C1 plus Q square upon 2C2 plus and so on. Therefore, W is equal to W1 plus W2 plus and so on. For parallel combination, W is equal to half CV square is equal to half V square into C1 plus C2 plus and so on. That is equal to half C1 V square plus half C2 V square and so on. That is equal to W1 plus W2 plus and so on. Therefore, W is equal to W1 plus W2 and so on. Thus, the total energy stored in both the types of combination is the summation of energies stored in each capacitor.